All right, so we are moving on from categorical logic to propositional logic, and let's get started. So, with categorical logic, what we were doing is we were abstracting away from the semantics of statements that are about relating two classes of objects. But there are tons of other statements out in the world. And so propositional logic is supposed to help us do the formal logic with all of these other statements. Just like with categorical logic, we're going to keep some of the meaning of our statements. So remember, with categorical logic, we have all SRP. We kept that all in there. We kept that R in there. Because if we got rid of the all and the R and we'd have just like SP, that wouldn't mean anything to us. It would, like, we wouldn't be able to use our logic. We wouldn't be able to do anything with that. So just like that, we are going to keep some of the language in our statements, and these are the logical connectives or the logical operators. And these are special symbols that can be used as part of our ordinary language statements. They're the basic elements. Without them, we wouldn't be able to do anything with our statements. So there are 5 kinds: negation, conjunction, disjunction, conditional, and biconditional. And you should be very familiar with negation, conjunction, and disjunction because you use them all of the time. These are probably some of the first words that you ever learned. Now, conditional, you should also be familiar with. Why? You read a little bit about it in chapter 1, but also because you use conditionals all of the time, especially when you're like planning your day. Maybe you're thinking, like, if I go to class, then I have to get up early. And if I get up early, then I have to set my alarm. And if I set my alarm, then I should probably go to bed late or earlier, So you use conditionals all the time. And now we're really going to dive into this like formal analysis of what a conditional is. Biconditional is probably going to be a little bit new for you, but that's okay. It's not that crazy. It's not that complicated. And you'll find out. All right, so within this logic, we're going to have simple and compound statements. A simple statement is just a proposition with one statement, so there's no logical operator. And when we abstract away from the meaning, what do? We get the entire statement and we replace it with a capital letter. So North Carolina is a state, we can replace that with N. Thank God it's Friday. We can replace that with a T. Strawberry ice cream is superior to all of their flavors. We can replace that whole thing with an S. Now, I know you got in this habit of replacing our subject and predicate with a capital letter, but now we're just going to be replacing entire statements with a capital letter. Because notice, none of these statements are categorical propositions. They're not relating to classes of objects. Compound statements are propositions with at least one simple statement and at least one logical operator, although most of them are going to have more than one simple statement. So it's not the case that Puma deserves to be judged for being a pit bull. We have this full statement. Puma deserves to be judged for being a pit bull. So we're going to give that a D. But then we have it's not the case, and that's representing negation. So we end up with it's not the case that D. And we have a logical symbol that we use to represent our negation, and that's that little squiggly line. Duke is a private school and UNC is a state school. So we have UNC, that's a full statement, we'll give it a U. Duke is a private school, that's a full statement, we'll give it a D. The and stays, so we end up with D and U. And our symbol for and is this dot, so we end up with D dot U. Either we can go to the football game or we can stay home. We have a full statement, we can stay home, we'll give that an H. We have a full statement, we can go to the football game, we'll give that an F. So we end up with F or H because our or stays. And we now change out that or with a symbol. So we end up with F or H, or we wanted to use the symbol language, F wedge H. If you eat a caloric surplus, then you will gain weight. So we have the statement, you eat at a caloric surplus, that's going to be given an E. We have the statement, you will gain weight, that will be given a W. So we end up with if E, then W. And our symbol for conditional is this thing called a horseshoe. It's like a sideward sideways C, so we end up with E horseshoe W. The order really matters for this one, the E and the W. You want the first part of the conditional to be first, and you want the latter part of the conditional to be at the end. The order does not matter as much for these two statements, or even down here. But down there, that's our biconditional. So we have the statement, you will be successful if and only if you follow all of the norms. So we have a full statement, you will be successful, we'll give that an S. We have a full statement, you follow all the norms, we'll give that an N. So we end up with S, if and only if N. And our symbol for if and only if is a triple bar. It's 3 lines. So here's a nice little chart that kind of summarizes what I just said. So we have the squiggly line for negation, that's a tilde, and it's used to translate any kind of negation. We have a dot for conjunction, the wedge for a disjunction, the horseshoe for a conditional, and the triple bar for our biconditional. All right, here's a natural stopping point, but I'm just going to keep on going. So I'm going to really break down these logical connectives, but like I just said, you're super familiar with like 4 of them because you use them all of the time. So this might seem like super slow, but it's better to be safe than sorry. So I'm going to go through it. So negation is used to deny the statement that follows whatever phrase is being used. So it's not the case that, or it's not that, or it is false that, or it's not true that. These are all intended to represent negation. So it is false that Puma's a cat. Puma's a cat is a full sentence, so we'll give it a C. And then we use our squiggly line, our tilde, to get this completely abstracted form, squiggle line, tilde C. Conjunction is a compound statement that has 2 distinct statements, or conjuncts is what we'll call them. It's connected by the dot symbol. Tons of ways to write a conjunction, and, both, but, still, moreover, while, however, also, although, yet, nevertheless, whereas. So I went to the store, but I forgot my wallet. It's actually an and statement. So we get S.W. and Val teach philosophy. Notice that's not written as like 2 grammatically correct statements combined with an and, but that's exactly what it is, right? It's saying Angela teaches philosophy and Valerie teaches philosophy. So we can write that as A.B. Disjunction is an or statement. You have or, either or, but also unless. And this is a compound statement that has 2 distinct statements, what we'll call disjuncts, connected by the wedge symbol. So Puma will come to the party unless there are children there. Puma didn't really like children. So we have a complete sentence, Puma will come to the party, that's P. We have a complete sentence, there are children there, that's C. So we end up with P or C. P wedge C. She's a Pisces or a Sagittarius. So again, that's kind of like the other one where it's not 2 complete sentences, but we can treat it like that because that's what the meaning is supposed to be. So we end up with, she's a Pisces, P, she's a Sagittarius, S. So we end up with P wedge S. And then July or August has 31 days. We end up with J wedge A. July has 31 days or August has 31 days. Now the thing about disjunctions is that in ordinary language, they have 2 meanings. They could either be exclusive or inclusive. An inclusive disjunction is a disjunction where it's possible that both disjuncts are true. So it's not necessary that they're both true, but it's possible. And then we have an exclusive disjunction, and that excludes the possibility that both are true. If one is true, then the other one can't be true. So suppose you go to Olive Garden and the waitress or waiter tells you you can have soup or salad, but not both. What they're trying to do with this phrase, but not both, is tell you that this is an exclusive disjunction, that you can have soup, but if you do, then you can't have salad. You can have salad, but if you do, then you can't have soup. But notice if the statement is written like that, you can have soup or salad, that's ambiguous. It could mean inclusive, but it also could mean exclusive. We don't know. We don't have enough information. So That's another problem. I keep telling you how hard translations are. It's because when we speak in ordinary language, we tend to just say ambiguous stuff all of the time. Now, to translate this, if we have a statement like this, then we're going to write it out like this. You can have soup or you can have salad, and it's not the case that you can have soup and salad. Now, some students might be tempted to write it out like this, but this would not be the correct way to write it out. And you might be thinking, oh, it's kind of like math where we have this negation. We can just push that negation through and distribute it to both conjuncts, but that is not, we cannot do that. This statement over here and this over here are not logically equivalent. We're going to learn about that later on when we start doing some more rules, what we can and cannot do when we, like what information we know given some statements, but this is not a move you can make. So this would not be the correct way to translate this. Now, if we had this statement, this ambiguous statement, you can have soup or salad, we're going to treat it as inclusive. And that's how we're going to treat all disjunctions when we finally get to the abstracted away version of it, where it's just S or D. That's what we're going to treat it as, S or D. The definition of a disjunction is that if a disjunction is true, then at least one disjunct is true. At least S is true, at least D is true. If neither are true, then this statement as a whole is going to be false. But just because S is true, we're not going to make the assumption that D has to be false. So if we did make that assumption, we'd be treating it as an exclusive, but we're not going to treat our disjunctions as exclusive. We're going to treat them as inclusive, where the truth of one does not necessitate the false, that the other is false. The truth of one, we don't know the truth of the other. Now, if one is false, we are going to be able to determine that the other is true, because like I just said, for disjunction to be true, at least one has to be true. But for the purposes of this class, just remember that we're treating all of our disjunctions as inclusive, where it's going to be possible that both are true, even though when we're looking at the semantic notion of disjunction, it is possible to have exclusive disjunctions. All right, conditionals. So you read a lot about conditionals in chapter 1, and I kept telling you, right, we're going to cover it later, and now we're covering it. So conditional is an if-then statement where whatever follows after the if is the antecedent, and whatever follows after the then is the consequent. So I'm going to continue to use these words antecedent and consequent because it's just easier that way. Now, conditional is not asserting the truth of the antecedent or the consequent. The semantic meaning is just that if the antecedent is true, then the consequent has to be true as well. Now, if the antecedent is false, we can't make any assumptions about what the consequent is. And if the consequent is false, we can't make any assumptions about the antecedent. All we know from a conditional is that if the antecedent is true, then the consequent has to be true. So if we have a true antecedent and a false consequent, then the conditional as a whole is going to be false. Now, conditionals can be written in many different ways. Here's a different way, right? And I talked about this last class when I was talking about the translations for categorical statements. So Puma will come to the party with me if, or Puma will come with me if I go to the party. Whenever I see a conditional written in not its typical if-then form, I immediately write it in the if-then form. So in this case, I have, if I go to the party, then Puma will go with me. So I have that down here. Why do I do that? Because when I abstract away, when I put it into this final symbolic form, I want to make sure the order is correct. If I leave it like this, where I have Puma will come with me as C, and I go to the party as P, I might be tempted to write this as this. And that would be wrong. This is not the correct translation of this or of this. So to avoid making that mistake, to avoid having the order of my P and C mismatched, not aligned with the correct semantic meaning of my antecedent and my consequent, I always make sure that if I have a conditional not written in the traditional form of if-then, I immediately go ahead and put it in that traditional form of if-then. Now, the book gives us all these different ways that we write conditionals, and there are actually more than just this way that we write conditionals. So keep that in mind. Again, translations are tough. So these are several different ways that conditionals are written. We'll cover more as we get to the translation section of this unit. But always, whenever I see something like this, I try my best to write it as the if-then form. Only if. So anytime I see the word or the phrase only if, I immediately cross out only if and I write then, because the semantic meaning of only if is then. Whatever follows the only if is the consequent. So I cross out only if and write then because students are often very tempted to treat whatever comes after the only if as the antecedent. Why? Because of the word if. They see the word if and they say, oh, whatever comes after if is the antecedent. But if we have only if, then actually what comes after is the consequent. So we have this statement, you will pass logic only if you study. I already crossed out only if and I wrote then. So the you study, that's the consequent. So we end up with if you pass logic, then you studied, and we end up with L horseshoe S. Now, if you had this initial statement and you saw the if and you're like, oh, what comes after the if is the antecedent, you might end up writing S horseshoe L, and that would be incorrect. So anytime you see only if, cross it out and write then. Down here, I had it as only if you try, will you succeed? But I'm already gonna like cross that out and write then. And I know by doing that, I end up with this horrible statement, then you try, will you succeed? And that's like, what does that even mean? Why do I do this? Because now I know that the you try is our consequent. So I can write then you try down here. That means whatever remains is the antecedent. So if you succeed, then you tried, and we end up with S horseshoe T. So be very careful when you see only if in our statement. Now, a conditional is supposed to represent a relationship between the antecedent and the consequent, where the antecedent is supposed to be sufficient for the consequent, and the consequent is supposed to be necessary for the antecedent. And what does sufficient and necessary mean? Sufficient means enough. So if I say this condition is sufficient for this other condition, what am I saying? I'm saying that this event is enough to ensure this other event, that the truth of the antecedent guarantees the truth of the consequent. So we look at an example. If you live in North Carolina, then you live in the United States. Living in North Carolina is enough to get us to live in the United States. It's sufficient for living in the United States. Like if you know that I live in North Carolina, then that should be enough information for you to say, okay, so you live in the United States. So not all conditionals imply a sufficient or necessary condition. There might be zero relationship between our antecedent and our consequent. And that's fine because once we get to the syntax, it doesn't matter. Like a syntax of a conditional, like a if P then Q or P horseshoe Q, you don't know whether the P is sufficient for Q. You don't know whether the Q is necessary for P. It doesn't matter. It's pure syntax. See, we can get conditionals like this. If today is Monday, then my dog is a blue heeler. There's no connection between the day of the week and my dog's breed. It's just a kind of like, I just randomly plugged in sentences there. Still a grammatically correct conditional, but there's no connection. There's no sufficiency or necessary conditions being uttered. So moving on to necessary conditions, the consequent is supposed to be necessary for the antecedent. And what does necessary mean? It means it's essential, it's mandatory, or it's required. So going back to that conditional that I had earlier, if you live in North Carolina, then you live in the United States. What this is saying is that living in the United States is necessary for living in North Carolina. That it would be impossible for you to live in North Carolina and not also live in the United States. Like, because imagine if I said that, if I was like, yeah, I live in North Carolina, and you're like, oh, so you live in the United States? And I'd be like, no, I just live in North Carolina. I don't live in the United States. That's like nonsensical, because living in the United States is a necessary condition for living in North Carolina. And here's another example. So my car starts only if I have gas. So notice I crossed out that only if and I wrote then. So now I know that I have gas is my consequence. So I get, if my car starts, then I have gas. So having gas is necessary for your car starting. But notice it's not sufficient, right? You need more than just gas in order to start your car. Like if your battery doesn't work, then your car's not going to start, even if you have a full tank of gas. So sometimes a necessary condition is not sufficient, but sometimes it is. And that's the messy part of language. Keep this relationship in mind. It's important when we're just thinking about the semantic content of conditionals. But once we move on to the pure syntax, when we're evaluating like our arguments and doing our proofs, this is not going to be as important. All right, a biconditional, if and only if. So this is the only logical connective that you might not be super familiar with. It's super, super common in philosophy. Why? Because when someone's giving or saying like a biconditional, what they're supposed to be doing, what the semantic meaning of that statement is supposed to be, is that this is the necessary and sufficient conditions for whatever we're trying to like define. So, if I were to say something like in philosophy, there's like, what's the definition of knowledge? And say, you have knowledge if and only if you have a justified true belief. That's what that is supposed to represent, this necessary and sufficient condition for knowledge. But again, not always. Why? Because not everybody's a philosopher, and a lot of people use this phrase incorrectly. Basically, a biconditional is a conjunction of two conditionals, one indicated by the if and the other indicated by the only if. And that's why, look at, only if is supposed to represent then. So we have if, that's one part of our conditional, only if, that's the other part of conditional, and so a biconditional is just a conjunction of two conditionals. Let's work through the example. You will pass this class if and only if you do all of the assignments. What is that supposed to represent? It's supposed to represent that if you do all the assignments, then you pass this class, and if you pass this class, then you do all the assignments. Basically, in this statement, we have passing the class is necessary for doing all the assignments, and doing all the assignments is sufficient for passing the class. Down here, we're saying that passing the class is sufficient for doing all the assignments, and doing all the assignments is necessary for passing the class. So that's what I'm saying, that this biconditional is representing this necessary and sufficient condition, because it's a combination, it's a conjunction of two conditionals. So down here, I have that written out. If you pass this class, you did all the assignments, and if you do all the assignments, then you pass this class. So we would, if we were to write that in just the logical form, we'd get P horseshoe L and L horseshoe P, but we can also write that as our biconditional, P triple bar L. And when we do the truth tables in a little bit, this is going to make a lot more sense. All right, another stopping point, but I'm going to keep on going. So when we're thinking about our compound statements, what we're really trying to do is formulate with, which is a well-formed formula. And this is an arrangement of our operator symbols such that the resulting symbolic expression is grammatically correct. So we want correct syntax. Now, just like with our categorical logic, where the scope of the quantifier really mattered, here the scope of the logical operator really matters. So this is super, super important. And we're going to use parentheses to avoid ambiguity and to make sure that the scope properly covers what we want it to cover. So some rules to remember: when we have a dot, the and, or a wedge, the or the horseshoe, a conditional, or the triple bar, the biconditional, those have to go in between two statements. So you can't have something like this maybe like F horseshoe or F wedge. Like notice that we have a statement here, we have the wedge, but we don't have another statement. That would be a correct with. This wouldn't. So rule 2, the tilde goes in front of the statement it's made to negate. So incorrect to do this would be like F tilde like that. That's not a grammatically correct statement. We would need it to be like this. Rule number 3, the tilde cannot go by itself between two statements. So that would be something like this. That's a grammatically incorrect statement. We can't write, that's not a with, not a well-formed formula. So rule number 4, parentheses, brackets, and braces can be used to eliminate ambiguity in a compound statement. So check out all of this, the statement we have here. We have a bunch of wedges going on. We have a horseshoe over here. So we want to use parentheses in order to make sure that the meaning, the semantic meaning, is maintained in our syntax. So here we use parentheses to isolate that F or G, so we know that that's one disjunct of this main disjunct here. And on this disjunct, we have on one side a conditional, on the other side just an L. And then we use another set of parentheses to show that, all right, this is a disjunct for this. This is one side of our disjunct for this statement over here. You want to make sure your parentheses have an end. So don't have hanging parentheses. If you have hanging parentheses, it's going to mean that you've done something incorrect. You've made a grammatically incorrect statement. What do? Count your parentheses and make sure you have the same, an equal number on each side. So look, I have 1, 2, 3 left hand parentheses, and I have 1, 2, 3 right hand parentheses. If I had this, then I would have 1, 2, 3 left-hand parentheses, but only 1, 2 right-hand parentheses. And this statement now it's ambiguous. It's not a grammatically correct sentence. So I have to make sure that I include that when I'm writing my sentence. All right, so then some more rules. Any statement letter standing alone is going to be a with. So if you have S, that's a with. That's fine. It's just a simple statement. If S is a with, then so is going to be tilde S. So not S, that's going to be a with as well. If S is a with and P is a with, then P dot S, P wedge S, P horseshoe S, or P triple bar S, they're all going to be withs as well. And then, of course, parentheses, brackets, braces are used to eliminate ambiguity in compound sentences, statements. So, big, huge, important part of this is identifying the main operator of a statement. And this is the operator that has the entire with as its scope. So it's always going to be either one of the 4 connectives. And there's always going to be one main operator. Always. So some examples. This first one, we have tilde R wedge Q. You might be thinking, what's the main operator here? Well, the scope of the tilde is just the R. And then we have a wedge with 2 statements on each side. So the wedge is going to be the main operator here. This one, we use our brackets to show that the main operator is the dot, this and. So we have the S on this side all by itself. On this side, we have a P or Q. If we didn't have the parentheses, that statement's ambiguous. We don't know what the main operator is. So we have to keep those parentheses in there so that we know that what the statement is saying, it's P or Q and S. Down here below, this one's crazy, right? Like, what's the main operator here? One way to think about this is to look for the operators that are not contained in brackets. Now, if we look at this, this is contained in a bracket, this is contained in a bracket, the dot's contained, that dot's contained, that dot is contained, this horseshoe is contained, but hey, this one's not contained in brackets, but neither is this one. So now we've narrowed down, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 logical operators in this statement, and we've narrowed it down to 2. So how do we know which one's the main operator? we look and we say, all right, this negation can't be the main operator because its scope does not cover that at all. The scope of that negation is just what follows it, which is this parentheses, P or M. So the main operator has to be that triple bar. Again, we're looking now at this bottom one. We're looking like, oh, what's the main operator? Maybe it's this one, maybe it's this one. But notice this one is contained within this set of parentheses out here. So the main operator has to be that negation. So a good hint to help you is to look for the operators that are not in parentheses, but it's not going to be enough because we're going to get cases like this. So it's important to keep in mind, what is the main operator of that negation? If it doesn't cover the whole sentence, then it's not going to be the main operator. So again, all of this is to avoid ambiguity. So take a statement like this: P or Q and R, it's ambiguous. So if we assign P, Paul will go to the party. If we assign Q, Queenie will go to the party. And we assign R for Ryle to go to the party, we end up with two different possible meanings for this statement. It's either going to be this one, where the P or Q is on its own as it's a conjunct, and then R is the other conjunct, or it's going to be this one, where P is one disjunct, and then Q and R is the other disjunct. So the first meaning is saying that Paul and Raul will go, or Queenie and Raul will go, or all three are going to go. The second meaning is saying that Paul is going to go alone, or Queenie and Raul will go together, but not Paul, or all three are going to go. So notice radically different meanings just because we don't have parentheses around here, and we have to assume which one is the speaker trying to say, this one or this one. So when we're constructing our syntax, we have to make sure that we keep parentheses so we avoid this kind of problem. All right, translations. So one translation that we haven't covered yet is neither nor. So a sentence, I never know if it's neither or neither. Neither it is raining, nor is it sunny. What's that saying? It's actually saying it's not the case that it is either raining or sunny. So it's not the case either or. The either or is going to be translated just as we have, F or Q, and we're saying it's not the case. So we need that negation. We're saying it's not the case the entire statement. So we end up with tilde, parenthesis, F or Q. So we're going to go through some examples of translations, but my hint for translations is just to take it one step at a time. So don't go too crazy, like don't get all worried or overwhelmed. Like, look, this is a lot. There's a lot going on here. Let's work through it together. So it's not the case that you will eat a lot of salads. So wait, oh, there's an if in there. It is not the case that if you will eat a lot of salads, then you will absorb a lot of vitamins. And it is not the case that if you will absorb a lot of vitamins, then you will eat a lot of salads. Now, I'm going to say here that normally we're using a dot as our conjunction, but there is no dot on my keyboard that will allow me to use it. So I'm going to use this as my and. Likewise, there's no horseshoe that I can use for my my horseshoe. So what I'm going to use is this, the greater than sign. Now that's only because I'm on a computer. If this was like an in-person class, then I could easily write the dot or write the horseshoe, but I can't right now. All right, so what I'm going to do first is I'm going to highlight all of the logical operators. So it's not the case, that's a not. If, that's a if then. But if then here, if my computer would work with me. And another one. It is not the case. I have another negation. I have another if here. So there's the then. And I'm thinking that's it. So it's not the case that if you eat a lot of salads, then you will absorb a lot of vitamins. And it is not the case that if you will absorb a lot of vitamins, then you will eat a lot of salads. All right, so I have all my logical operators. Now I'm gonna start assigning some letters to my statements. So I have, you will eat a lot of salads. I got an S. And I know that's an if then, so I'm gonna go ahead and put S then absorb a lot of vitamins. So that's going to represent that. And then I have an and then I have it's not the case. Then I have another if then, and it says if you will absorb a lot of vitamins. I already gave that a V. This is a conditional, then you'll eat a lot of salads. Now I'm missing a negation up here in the front, so I'm gonna go ahead and put that. But I need parentheses, obviously. Like, look at all of this. This isn't gonna work if I don't have any parentheses. So when I see a statement like it is not the case, that's usually intended to negate the whole whatever follows it. Because if it wanted to just negate the antecedent, then the English statement would say something like, if you don't eat a lot of salads, then you will absorb a lot of vitamins. Notice the don't is embedded in the antecedent. So that's how I know that if I'm saying if it's not the case, that's going to cover the entire conditional. So I'm going to put one set of parentheses around that entire conditional. And now I know that this negation is going to cover that entire conditional. I don't know about the and yet, but I have another one of it's not the case that if you do this and that. So I know that negation is going to cover this entire conditional. Now I'm looking, and I think this is it. If I wanted this, it's not the case to cover the entire statement, including this and, then I would do this. But that doesn't seem to capture the meaning of the statement. It's not saying that it's not the case, all of this. It's just saying it's not the case, this conditional. So I don't think that extra set of parentheses is going to capture the meaning of this statement. Rather, I think that this is the proper translation of that statement. And what's the main operator? I look at which operators are outside of parentheses, and I have a not and not. The negation of the nots cover the conditionals. So the only thing left to be the main operator is that and. All right. Another one. But a spirit of harmony will survive in America only if each of us remembers that we share a common destiny. So what's going to be going on here? Go ahead and start highlighting my logical connectives, but only if. I think that's it. Now, remember when I said, when I see only if, I cross it out, and I write then. I did it that way because I didn't want the then to be crossed out. So now I have, but a spirit of harmony will survive in America only if then each of us remembers that we share a common destiny. So now I know that we have a conditional going on here, and that each of us remembers that we share a common destiny. I'm going to give that a D. That's going to be my consequent. So now I need to figure out what's my antecedent. But a spirit of harmony will survive in America. Now I'm starting to think that maybe this but is not intended to be a conjunction. Because what is it conjunct? Like, what's the conjunction here? I'd be missing some words. Something's missing over here. So that's just a funny way that language works out. A spirit of harmony will survive in America. That seems to be the antecedent. Give it an H. So now we end up with, if a spirit of harmony survives in America, then each of us remembers that we share a common destiny. So that's how I would translate that statement. But notice I had to make some judgment calls because it's not clear exactly what the purpose of this but was. I was treating it as a conjunction, but unless maybe I wrote this question incorrectly down, maybe there's more words that I was missing, but it seems like we're missing the other conjunct, right? A spirit of harmony will survive in America. That's a complete sentence, and there's no conjunction there. So I'm going to end up with that as my main Translation. So we're at another natural stopping point. If you want to stop now, it's a good place to do it, but I'm going to keep on going. So truth functional proposition. So the truth value of a compound proposition that uses one of the 5 logical operators can be determined solely on the basis of the value of each of its components. Basically, if we know the value of the parts of the statement, then we can figure out the value of the entire statement, of the compound statement. And how do we do this? We do this by using truth tables. So a truth table is an arrangement of truth values for truth functional compound propositions, and it shows every single possible case. So every single possible way in which these statements can be true or false, the truth table will show us this. And the truth value of the proposition is determined by the truth value of its simple components. And ultimately, we're going to be looking at the main operator to determine the truth value. But let's just go through each of our logical operators and look at our truth tables. So negation. So if we have a statement P, either that statement is going to be true or false. It can't be anything else. So when we're looking at our truth table and we have a not P, if P is true, then not P has to be false. And if P is false, then not P has to be true. That's just the definition of negation. So negation is pretty easy. Conjunction. So now we have to do more than just 2 rows. Because notice when we had a simple statement like P is either going to be true or false. There's no other possible combination of true or false for P. But when we have a conjunction, we have 2 simple statements, P and Q. And in some worlds, both P and Q are true. In another world, P is true, but Q is false. In a different world, P is false and Q is true. And in a different world, both are false. So we have to determine the number of rows that we have in order to construct a proper truth table. And how do we determine the rows? We have this formula. L equals 2 to the n, where L is the number of lines and n is the number of simple propositions. So now we have 2 raised to the n is the number of propositions. So we have 2. So we have 2 squared, and what's 2 squared? 4. So now we know that the number of rows is going to be 4. So how do we figure out what to put in for the columns? Like, how do we figure out like T's and F's down here? You take your first column, and we already determined that we need 4 rows. So this first column is going to have 4 rows divided by 2. And what's 4 divided by 2? 2. So I know I'm going to get 2 T's and 2 F's. Then I go to my next column. If I put 2 T's and 2 F's, now I'm going to do 1 T and 1 F, 1 T and 1 F. So your last column should always be that rotating TF, TF, TF if you've set up your truth table properly. And why are we doing this? Because we want to assess every single possible combination of truth values of our P and Q. And this is every single possible truth value. Now, for a conjunction to be true, both conjuncts have to be true. If one conjunct is false, then the conjunction as a whole is false. And think about that, right? This is how we use conjunction. If I say, I graduated from Duke and I'm from Florida. It's true that I graduated from Duke, but it's false that I'm from Florida. So if I were to say that, if I said I graduated from Duke and I'm from Florida, I'd be lying to you. Like, that would be a false statement. Now, if I said I graduated from Duke and I'm from New Mexico, that's true because I graduated from Duke, that's true, and I'm from New Mexico, that's true. So for a conjunction as a whole to be true, both conjuncts have to be true. And that's what this first row represents. We have a true P, true Q, so this conjunction as a whole is also going to be true. In the second row, we have a true P but a false Q. Conjunction as a whole is going to be false. Third row, we have a false P, true Q. Conjunction as a whole is going to be false. And then the bottom row, where both P and Q are false, the conjunction as a whole is going to be false as well. So earlier I said that the order of our conjunction doesn't matter, and this is going to show us why. So I have here A and O, and then on this other side I have O and A. Notice that the truth values under the main operator, which is the and here, are exactly the same. We have T, F, 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 and then over here we have T, F, F, F. When the value under the main operator is exactly the same on our truth table, like this, we can say that these two statements are logically equivalent. So if we look at this example here, Sherry got her IRS refund and bought a TV. That's logically equivalent with Sherry bought her TV and got her IRS refund. Now, from a semantic point of view, you might be thinking, the second one doesn't really make sense. The first one does, right? You get a refund from the IRS and you use that money to buy a TV. So there's like some like temporal relationship between getting the money and then buying the TV. But from a logical point of view, it doesn't matter. They are logically equivalent. Why? Because their truth values under the truth table for their main operator are exactly the same. So for a conjunction, the order of our simple statements does not matter. Same thing's going to be for disjunction as well. So disjunction. P, I'm going to assign I go to Duke. Q, I'm going to assign I teach logic. And I said earlier that for a disjunction to be true, at least one disjunct has to be true. So if we look at this first row, I go to Duke. Let's say this was like 4 years ago. That would have been true. I teach logic. 4 years ago, I was teaching logic at Duke, so that would be true. And so this disjunction as a whole would also be true. Now, let's say it's 5 years ago in my first year, or I don't even remember when my first year at Duke was. It might be like 7 years ago. It would be true I went to Duke, but your first year at graduate school, you don't have to teach, so it'd be false that I was teaching logic. Despite that, the disjunction as a whole is still true because my first disjunct, that P, is true. Now, let's talk about today, right? So I don't go to Duke anymore. I graduated. That's false. But it's true. I teach logic. I'm doing it right now. Disjunction as a whole is still going to be true. Now we can go back like 15 years ago. So 15 years ago, it was false that I was going to Duke. I wasn't at Duke at the time. And it was false that I was teaching logic. I was not teaching at the time. So 2 false disjuncts. That's the only time a disjunction is false, is when both are false. Otherwise, if at least one's true, it's going to be true. If both are true, it's still going to be true. Just like the conjunction, order of our disjuncts does not matter. If I did a truth table with Q or P over here on this side, I would end up with the exact same truth table. Conditional. So this one's a little bit trippy for some students. There's only one case when a conditional is false, and that's when we have a true antecedent and a false consequent. So this second row. Now, when both our antecedent and our consequent are true, the conditional as a whole is going to be true as well. When we have a false antecedent but a true consequent, we're going to get a true conditional. Let me think of an example. So if fire is present, then oxygen, if there's fire in the room, then there's oxygen in the room. Why? Because it's impossible to have a fire without oxygen, right? Oxygen is necessary for fires. So if there's a fire in the room, then oxygen is present. It's false that there's a fire in this room. At least right now where I am, I don't have any candles lit. There's no fireplace, so that's false. But it's true that oxygen is present. I'm breathing, right? So it has to be true. Just because it's false right now that there's a fire in the room doesn't mean that the conditional as a whole is false. Why? Because if there were fire, then there would be oxygen. The conditional is still going to be true, even though we have this case of a false antecedent. Same thing for this bottom row, and this bottom row is kind of trippy too. So if it's raining, then it's cloudy. That's a true conditional. But right now it's not raining here where I'm at. And right now it's not cloudy here where I'm at. So both of those, antecedent and consequent, are false. Despite that, it's still true that if it's raining, then it's cloudy. It just so happens that it's not raining, and it just so happens that it's not cloudy. So important row to remember for the conditional is this second one, where you have a true antecedent but a false consequent. That's the only case where you're going to get a false conditional. So let's think of another example. So if you live in North Carolina, then you live in the United States. So imagine it's true you live in North Carolina, but it's false that you live in the United States. Like, that's like incomprehensible. And why is that incomprehensible? Because the conditional as a whole is true. So it'd be crazy to think that it could be true that you live in North Carolina, but false that you live in the United States. Think of another example. If it's raining, then it's cloudy. So imagine it's true that it's raining, but it's false that it's cloudy. Like, that is breaking the laws of nature. It's impossible to have rain without clouds. So it's this row, true antecedent, false consequent, that we end up with the false conditional. So what are the things to remember with conditionals? That if the antecedent is true, then the consequent has to be true. Otherwise, the conditional is not going to be true. But it's not asserting that the antecedent is true. Just that if it is true, then the consequent has to follow. It also is not asserting that the consequent is true. And why? Because if we look at our truth table, look at this row, right? We have a true conditional, if P then Q, but it's not asserting the truth of the antecedent. In this row, the antecedent is false. And then if we look at these two rows, we have two cases where our consequent is true in the first and the third row, but in one case the antecedent is true, in the other case the antecedent is false. So just because the consequent is true doesn't mean we can say anything about the antecedent. Just because the antecedent is false doesn't mean we can say anything about the consequent. Only when we know that the antecedent is true can we say something certain about the consequent, namely that it has to be true, or else the conditional as a whole is going to be false. All right, biconditional. So earlier I told you that a biconditional is just a conjunction of two conditionals, one where we have an if P then Q, and where we flip our antecedent or consequent, we get if Q then P. So in this case, when both P and Q are true, we end up with a true biconditional. And when both P and Q are false, we end up with a true biconditional. But in cases when we have a true P and a false Q, or a false P and a true Q, we end up with false biconditionals. Now, I didn't write this up here, but we can show this. Let me write it over here. So let me draw. I'm going to put Q horseshoe P over here on this side. And I'm going to do the truth table down here. So true Q, true P is going to be a true conditional. False Q and a true P is going to be a true conditional, because false antecedent, true consequent is going to give us a true conditional. And here we have false antecedent, true consequent. Down here we have a true antecedent and a false consequent. So that's the only time when a conditional is false. And then down below, both are false, and that's going to be a true. That's going to be a true conditional as a whole. So now I have my truth values for my main operator for the if P then Q, and I also have the truth values for my main operator for if Q then P. And I just said a biconditional is a conjunction of these two conditionals. So we'll go ahead and put a dot here. Now let's figure out what the truth value of this column is. Well, this one's T, that one's T. For a condition or a conjunction to be true, both conjuncts have to be true. Down here I have an F and a T, and remember, if one of our conjuncts is false, then the conjunction as a whole is going to be false. So that's F. So that's F. Down here I have true conjunct on this side, but a false conjunct on that side. So that's going to make this conjunct as a whole false. And down here I have true conjunct on this side, true conjunct on this side. So that's going to be true. And notice TFFT, that's the exact same as here, TFFT. So this truth table is showing us that if P then Q and if Q then P is logically equivalent with P triple bar Q. They have the exact same truth values under the main operator of the statement. So that's my proof to you that a biconditional is just a conjunction of two conditionals. So if both P and Q are true, then both conditionals will be true, which is going to make this conjunction true. If both P and Q are false, then both conditionals are still going to be true, which is going to make this conjunction true. And that's what that truth table is intended to represent. All right, another natural break. This is a long video, I know. We're almost done. Take a break if you need it, but I'm going to keep going on. All right, so sometimes where the values of the simple state are given to us. So up above here, we had to come up with all of the different possible values for P and Q in order to come up with the values for this one. Here, the values are given to us. So we know that P is true and we know that Q is false. And now we need to figure out what's the true value of this statement, P or not Q. So we just get a shortened truth table. It's just easier for us. So we know that P is true. So I'm going to put a little T over here to like remind myself that this P is true. But notice I'm trying to find the truth value of the main operator. So this is another reason why figuring out what the main operator is so important. And remember I told you, what's the way to figure out what the main operator is? You figure out which operator is not in parentheses. And here's an example of, we have two main operators and neither of them are in parentheses. So now I have to look at like the scope of each logical connective. The negation scope is going to cover this Q, but it's obviously not going to cover the P because that would be like it would be an improperly formulated formula. So I know this negation covers the Q, but not the P, which leaves this wedge as our main operator. All right, so I know that P is going to be true. Now I know that Q is false, but I need to know what not Q is. And if Q is false, then not Q has to be true. Now I have the value of this P and I have the value of this not Q. And now I need to figure out the value of this OR, this wedge. And if what's the value for an OR? I can either go up here and go ahead and look, right? So if I have a true P and a true Q, then I gotta get a true OR statement. The disjunction as a whole is going to be true. But that's another way to just think about it, that I know that for a disjunction to be true, at least one disjunct has to be true. And since P is true here, then I know for sure that this disjunction is going to be true. I don't even need to know what not Q is. But I do know what not Q is because I know that Q is false. So this statement as a whole, the value is going to be T. Another example, so in this case, R is given to me, I know it's true. S's value is given to me, I know it's false. And P's value is given to me, I know it's true. Now I need to figure out what the value of this entire statement is. So it's order of operation. I have to kind of work my way backwards because I want to know what this main operator is. And how do I know that's the main operator? Well, it's the one outside of the parentheses. This one inside the parentheses tell me that that dot only covers that S and P. So this horseshoe has to be my main operator. Now, I know that my R is true. So I'm going to put a little T there just to remind myself that's not the one that I need to look at when I'm trying to make the final assessment, but it's just there for a reminder. And then now I'm going to look at S and P. So S is false, P is true. What was the rule with conjunction? That for a conjunction to be true, both have to be true. If one of our conjuncts is false, then the conjunction as a whole is going to be false. So I know that that's going to be false. So now I have the value of my antecedent right here. And I have the value of my consequent right here. So I have a true antecedent and a false consequent. Now I can either think about, I've memorized the rules, or if I haven't memorized the rules, I can like go up here and look and say, all right, true antecedent, false consequent, that gives me a false conditional. True antecedent, false consequent, that means the main operator here, this horseshoe, has to be false. So when the values are given to us, it just helps us out. We don't have to do as much work. So truth tables for propositions where the values are not known. The step one is to find out how many rows you need to make. So if I have this statement here, P and Q or Q, what's my formula? It's L is equal to raised to the N, where L is a line and N is the number of simple statements. Now you might think, oh, I have 3 simple statements. That's not true. I only have 2. I have the P and I have the Q, because Q occurs twice. So 2 times 2 equals 4. So I know I'm going to have to make a table with 4 rows. Now, truth tables are a mechanic way to figure out the truth value, but there's a flaw to this. For one, if you don't draw your truth tables properly, you can misread them. So just like with the Venn diagrams, if you didn't draw them right, you might misread them. Same thing for the truth tables. If you don't draw them right, you might misread them, and you might make a mistake, and then you get the wrong answer when you otherwise wouldn't have. But another problem is that the more simple statements we have, the bigger the truth table is going to be. So if you have a statement that has 4 simple propositions in it, you have to do 2 raised to the 4, which is 2 times 2 times 2 times 2, and now you have a truth table with 16 rows. That's crazy, right? So let's do it. Let's do this one first, and then I'm going to show you just how difficult it gets. So when you're figuring this all out, just make sure you use order of operations. And what does that mean? It means the order of handling the logical operators within the proposition. So the main operator is always going to be the last step, and that's really the only column that matters. So if you can do all of the side statements on your own, like you don't have to write them out, that's fine. You can do it in your head, because the only column that really matters is the main operator. So I don't need to see all your work when you're doing these truth tables, but if you're not comfortable, you should absolutely fill out the entire truth table, because you're just going to get confused. All right, so let's work through this example. So we have, it's not the case, P and Q or Q. Never really filled out this side, because again, we only have 2 simple statements. So this left-hand side of our table is going to look the exact same, where we have TT, FF, TF, TF. I'm going to do one with 6, or I'm going to show you one with 6 to just show how crazy it gets, or 8 and then 16. So we have this big statement. I need to identify what the main operator is. It's either going to be this negation or this or. But I have parentheses that cover this P and Q, so I know that this negation is going to cover this conjunction, not this Q over here. And a way to figure this out too is to match up your parentheses. So I only have 1 pair of parentheses here, so I go left and I match it up to that right one. And I'll show you how to match it up with the larger widths as we move along. All right, so I want to break this down. I know Q's values, they're over here, but I'm going to write them over here too, because and I'm going to write them small, so that indicates to me that this is not my main operator. This is just to help me figure out my main operator. This is the main operator, this wedge, so I'm going to leave this one blank for now, because I need to figure out what's going on here. Now, do you want to start with the not, or do you want to start with the and? You're going to want to start with the and, because this is saying it's not the case, whatever's all going on in here. So I need to figure out what's going on in here before I can figure out the negation of it. So let's figure this out. P and Q. Well, I already told you guys that for a conjunction to be true, both conjuncts have to be true, and that's only going to be in that first row, because in the second row, Q is false, in this third row, P is false, and in this last row, both are false. So now I have the values of P and Q, but I'm not done yet. I need to figure out the values of the not. So I go over here, and if P and Q is true, then not P and Q is going to be false. If P and Q is false, then not P and Q is going to be true. So these values align with this negation. So now to figure out the main operator, I need to figure out this wedge. But what values am I at? I'm going to be looking at this negation and this Q. So how do I do that? Remember, with the disjunction, for it to be true, at least one disjunct has to be true. So on this case, I have Q is true. That means that's going to be true. In this row, Q is false, but this not negation over here is true. So that's true. In this case, both are true. So I have a true statement. And in this case, although this Q is false, this negation over here is true. And so those are the main, those are the truth values of the main operator. This statement is always true, no matter what combination of T's and F's we have for our P and Q. Not the case P and Q or Q is always going to be true. So now imagine though, this one we have two simple statements. Imagine if we had three simple statements. So our formula would be 2 raised to the 3. So that's 2 times 2 times 2. So we get a truth table with 8 different rows. And that's what this would look like. Now to figure out how to plug in my T's and F's over on this side, I get my first column and I have 8 rows. So 8 divided by 2 is 4. So I put 4 T's and 4 F's. Now I'm going to split that in half again. So if I put 4 T's, the next column is going to be 2 T's, 2 F's, 2 T's and 2 F's. And then I split that in 2 again. So 2 divided by 2 is 1. So then I get T, F, T, F, T, F, T, F. So already this truth table is getting big. It's getting large. And the bigger they are, the easier it is to make mistakes. Even though, like I said, this is an entirely mechanical process. Like a computer would never make mistakes if you plugged in the values properly. But we are not computers, so we can make mistakes. So this example is already showing us what the main operator is. It's this wedge. It's the one outside of the parentheses. So I need to figure out what's in that column. P is easy. I already have P's value over here, but I need to unpack this one over here. So do I want to start with this and? No, I don't, because I'm comparing R with not S. So I want to start with this not S first. So if S over here is true, then not S is going to be false. It's T, T, F, F, T, T, F, F. So I end up with F, F, T, T, F, F, T, T. So now I need to compare that negated S's values with this R over here. And I'm doing a conjunction. So I got to remember that for a conjunction to be true, both conjuncts have to be true. I already see that I have 2 F's here, so I know that the conjunction can't be true in the first 2 rows. I have 2 T's over here, so now I have to go look at my R and see, oh, they're both true over there. So I end up with 2 T's here. These are both falses, so I know this conjunction's got to be false. These are both true. I got to go look at my R, but hey, on my R side, they're both false down there. So that means that conjunction is going to be false down here. So these are all the values of this conjunction, but I'm not done yet. Now I have to compare the values of this conjunction with P, because P is my other side of my formula. And in this case, it's a wedge. So what do I want for my wedge? I need at least one true disjunct. Here, I have an F, but if I go look at my P, it's true, so I get a T. Here, I have an F. If I go look at my P, it's false, so I know that's going to be an F. Here's true, so I know it's got to be true. Here it's true, I know it's got to be true. Here it's false, but I just need one true one, so let me go look at my P, and hey, that's true, so that's going to be true over here. This is false. I go look at my P in that same row. That's false, so this is going to be false. This is false. I got to go look at my P. It's true, so that's going to be true. And then this last row, this conjunction is false. I go look at my P. It's false as well, so that's going to be false. And this is all of the values for this statement. Take your time with the truth tables. Trust me. Like, you don't want a messy truth table and then you're trying to read it and you can't because it's messy. Up to this point, we've just been putting out the values, but you're going to use these truth tables to figure out whether statements are tautologies or self-contradictory, or you can compare two statements to see whether they're logically equivalent. We've already done that. And later on, we're going to use truth tables to see whether or not arguments are valid or invalid. And for those ones, you really, really have to be careful about making sure your rows line up, making sure you're reading the right column when you're making the assessment for your main operator. Now, I'm not going to walk through this one, but I did want to show you when you have 4 simple propositions in a statement, you end up with 2 raised to the 4, which is 2 times 2 times 2 times 2, and that gets us 16. And this is what that looks like. Look at that. Look at all those rows. Look at all those columns. It's so easy to make a mistake with this. Not a mistake that you like accidentally misread a conjunction, or you're actually accidentally assigned a disjunction as false when you had at least one true disjunct in there. No, you're making mistakes because maybe you're reading these two and then you accidentally go sideways and you read the wrong column. It's just so easy to make just a mistake that has nothing to do with your logical ability and just everything to do with, like, we're not computers and we're not perfect mechanical machines. So this is a fatal flaw of the truth tables, is that when we get statements with 4 simple statements, here we have a P, Q, R, and S, we end up with these really, really large diagrams, and it's easy to make mistakes. All right, so a lot of material this week because you have your second quiz as well, but pace is picking up. If you're lost now, I really, really need you to meet with me because it's just going to get faster from here on out. All right, that's it for today.